Here's something that sounds impossible but works exactly as described. Special materials installed within standard wall assemblies absorb enormous quantities of heat during daytime hours when outdoor temperatures climb, then release that stored heat during nighttime hours when conditions cool. The absorption and release happen through phase changes between solid and liquid states at carefully selected temperatures matching interior comfort requirements. A typical installation stores 5 to 20 times more heat per unit volume than conventional thermal mass materials like concrete or masonry. The practical result is homes that maintain comfortable interior temperatures across daily cycles with minimal or zero active cooling operation. This isn't theoretical technology or future possibility. Phase change materials have been incorporated into building assemblies across thousands of residential and commercial projects over recent decades. The performance data consistently shows substantial cooling energy reductions, often eliminating cooling requirements entirely in appropriate climates and applications. Understanding how phase change materials actually function, what applications suit them, and what limitations apply, provides insight into a technology that remains remarkably underutilized despite proven effectiveness. The basic physics of phase change materials involves the substantial heat absorbed or released during transitions between solid and liquid phases. Water transitioning from ice to liquid at 32 degrees absorbs 144 BTUs per pound, an amount approximately 144 times greater than the heat required to raise liquid water 1 degree. This latent heat of fusion represents stored energy that doesn't change temperature during the phase transition. Specialized phase change materials designed for building applications use organic compounds, inorganic salt hydrates, or eutectic mixtures that transition at temperatures around 72 to 78 degrees, rather than water's 32-degree transition. The building application phase change temperatures match typical interior comfort ranges, allowing the phase transitions to occur within normal indoor temperature conditions. The implementation approaches for phase change materials in building construction have evolved substantially since initial commercial applications in the 1970s. Early implementations used bulk containers of phase change materials embedded within walls or ceilings. Subsequent developments produced encapsulated materials with phase change compounds contained in small polymer capsules mixed into drywall, plaster, concrete, or other matrix materials. Contemporary products include dedicated phase change panels, phase change sheets that install behind drywall, phase change integrated concrete, and various other product forms designed for straightforward construction integration. Wolfgang Hartmann, a German building scientist who has extensively researched phase change material applications across European construction, has documented performance patterns from over 200 residential and commercial installations. His research shows that phase change material installations with appropriate sizing and climate matching typically reduce peak cooling loads by 30 to 60% and reduce total cooling energy by 25 to 50%. The performance varies with specific climate conditions, building characteristics, and material selection, but consistent substantial benefits appear across the diverse installations he has monitored. The climate suitability for phase change materials follows specific patterns that affect application success. Climates with substantial daily temperature swings produce ideal conditions for phase change material effectiveness. Daytime heat absorption and nighttime heat release match the temperature cycling that drives phase change performance. Climates with minimal daily temperature variation produce limited benefits, since the daily cycling needed to complete the absorption-release cycle doesn't occur naturally. Matching application climates to daily cycling patterns proves essential for realizing expected benefits. The positioning of phase change materials within building assemblies affects performance substantially. Interior side installation immediately behind wall finishes provides direct interaction with interior air and thermal conditions. Exterior side installation within wall cavities produces weaker interior effects. Ceiling installation captures heat rising from interior spaces effectively. Floor installation provides thermal storage interacting with interior air through radiation. The positioning decisions affect both initial cost and performance outcomes, with thoughtful integration producing better results than generic installation approaches. Catherine Blackwood, an architect specializing in sustainable residential design, has incorporated phase change materials into 38 homes across various American climate zones over the past decade. Her design approach uses phase change panels installed behind drywall in ceiling and upper wall positions where they interact effectively with warm air accumulating in those locations. Her documented performance shows cooling energy reductions of 35 to 55% compared to identical homes without phase change materials. The reductions translate to typical annual cooling cost savings of $350 to $700 in warm climate installations. The material options for contemporary phase change applications provide flexibility matching different performance and cost objectives. Paraffin-based organic phase change materials offer chemical stability, adjustable phase change temperatures through specific compound selection, and moderate costs. Salt hydrate materials offer higher thermal storage capacities at potentially lower costs, but can experience stability issues across extended operation cycles. Bio-based phase change materials derived from vegetable oils provide renewable source alternatives. Eutectic mixtures combining multiple compounds allow customized phase change characteristics for specific applications. Each material category suits different priorities and application contexts. The cost analysis for phase change material installations varies substantially based on product selection, installation method, and project scale. Basic phase change drywall products typically cost $3 to $5 per square foot premium compared to standard drywall, translating to $2,000 to $4,000 of additional material cost for typical home installations. Dedicated phase change panel systems cost $8 to $20 per square foot installed, representing larger investments appropriate for maximum performance applications. The operational savings of $300 to $800 annually produce payback periods of 4 to 12 years, depending on specific implementation costs and local climate conditions. The historical development of phase change technology for building applications traces back to NASA research conducted during early space program periods. Temperature control requirements for space vehicles drove development of materials that could absorb and release heat within specific temperature ranges. Subsequent adaptation of these materials for building applications began in the 1970s and accelerated through successive decades. Contemporary products represent substantial refinements over early applications with improved performance, extended operational lifetimes, and reduced costs compared to first-generation technologies. Maxwell Reinhold, a materials scientist specializing in thermal energy storage, has documented how phase change material performance evolves across extended operational cycles. High-quality phase change materials in appropriate applications maintain performance characteristics across 30 to 50 years of daily cycling without significant degradation. The longevity matches building lifespans adequately for the materials to function as permanent building components rather than consumable equipment requiring replacement. The durability represents important progress over earlier generations of thermal storage technologies that showed performance degradation over much shorter time frames. The combination with conventional thermal mass produces enhanced performance beyond either approach alone. Phase change materials provide high thermal storage density within narrow temperature bands. Conventional thermal mass materials provide thermal storage across broader temperature ranges at lower density. Combining both approaches captures the benefits of each while mitigating their individual limitations. Contemporary high-performance residential designs increasingly combine phase-change materials with conventional thermal mass to optimize overall thermal performance across diverse daily and seasonal conditions. The acoustic and vibration dampening benefits of phase-change materials provide secondary advantages beyond pure thermal performance. The liquid phase during heat absorption periods dampens acoustic and vibration transmission that solid materials would conduct. The effects are modest but measurable, producing quieter interior environments in homes with substantial phase-change material installations. The secondary benefits add to overall performance value without requiring separate design considerations. Now for the obstacles and limitations that affect phase-change material applications. First, the initial cost premium compared to conventional construction represents a meaningful barrier for cost-sensitive projects. Phase-change material installations typically add $2,000 to $8,000 to typical residential construction costs. While payback periods from operational savings are reasonable, the upfront cost increase prevents some applications despite favorable long-term economics. Second, the climate dependence limits effective applications to regions with appropriate daily temperature cycling. Humid tropical climates with minimal daily temperature variation produce limited benefits from phase-change materials. Very cold climates with continuous cold conditions during heating seasons produce limited benefits since the heat release conditions don't persist consistently. Understanding specific local climate patterns proves essential before committing to phase-change material installation. Third, the material stability concerns require attention during product selection. Different phase-change material chemistries show different stability characteristics across extended operation. Organic paraffin-based materials generally maintain performance reliably across expected building lifespans. Salt hydrate materials have historically shown some stability issues that require specific formulation approaches to address. Selecting materials from established manufacturers with documented performance histories addresses stability concerns effectively. Fourth, the integration with conventional construction practices requires specific attention that standard construction teams may not possess. Ensuring proper positioning of phase-change materials, avoiding damage during construction, and integrating with surrounding building elements requires understanding that standard construction practices may not provide. Working with contractors experienced in phase-change applications or providing appropriate training addresses these concerns, but requires specific effort. Fifth, the performance verification challenges for phase-change installations exceed those for conventional construction elements. Visual inspection cannot confirm phase-change material performance in the same way it confirms insulation installation or air sealing quality. Performance verification may require specialized testing equipment or extended monitoring periods to confirm that installations are delivering expected performance. Homeowners should understand these verification limitations when evaluating phase-change investments. Despite these considerations, phase-change materials offer proven performance for appropriate applications. The combination of substantial thermal storage capacity, compatibility with standard construction methods, and reasonable economic returns makes these materials worth considering for new construction and major renovation projects in appropriate climate zones. The research trajectory for phase-change material applications continues producing improvements that extend the technology's applicability. Lower-cost materials reduce application economics favorably. Improved encapsulation technologies extend operational lifetimes and improve safety characteristics. New product forms simplify construction integration. Enhanced phase change temperatures match specific application requirements more precisely. The continuing research supports expanding applications beyond current boundaries while improving performance for existing applications. The building code recognition for phase change materials varies substantially across jurisdictions. Some building codes explicitly recognize phase change materials and provide performance credits for their installation. Other codes remain silent on these materials, neither encouraging nor prohibiting their use. Some codes create obstacles through requirements that assume conventional construction without accommodating alternative approaches. The evolving code recognition reflects the technology's growing acceptance, but creates application challenges in jurisdictions with less developed recognition. The indoor air quality implications of phase change material installations generally prove favorable compared to conventional construction. Sealed encapsulated phase change materials don't release compounds into interior air during normal operation. Some bulk applications can release trace compounds during phase transitions, though typically at levels well below health concern thresholds. Selecting products with documented air quality performance ensures that installations don't create concerns despite their substantial mass within building assemblies. The fire performance of phase change materials has received substantial attention given the organic chemistry of many formulations. Properly formulated and encapsulated phase change materials meet applicable fire safety requirements for building installations. Fire retardants added to formulations address flammability concerns that unprotected paraffin compounds would create. Testing documentation for quality products confirms compliance with building code fire safety requirements. Homeowners should verify fire performance documentation for products under consideration to ensure appropriate safety performance. Francesca Delacroix, a sustainable construction consultant based in Nevada, has documented case studies from 52 residential projects incorporating phase change materials across southwestern climate conditions. Her documentation shows typical summer cooling cost reductions of 40 to 65% compared to identical homes without these materials. The performance data confirms that hot, arid climates with substantial daily temperature swings produce ideal conditions for phase change material effectiveness. The cumulative savings across these installations demonstrates the genuine performance that motivates continued adoption and development. The combination with smart home control systems enables sophisticated optimization of phase change material performance. Systems that monitor interior conditions, outdoor forecasts, and phase change material state can coordinate ventilation, window operation, and other building systems to maximize the benefits that phase change materials provide. These integrated approaches achieve performance levels that passive implementations cannot match, though require additional investment in control equipment and integration expertise. The research at various American universities has contributed substantially to understanding how phase change materials function within building systems. Studies at University of California, Berkeley documented the wide thermal behavior of specific products across extended monitoring periods. Research at Oak Ridge National Laboratory characterized material properties and evaluated product durability under accelerated aging conditions. Collaborations between academic researchers and product manufacturers have refined both materials and application methods. The accumulated research provides strong technical foundations for informed product selection and application decisions that earlier generations of adopters couldn't access. The specific application in ceiling installations has emerged as particularly effective for cooling-dominated applications. Hot air naturally rises in interior spaces, accumulating at ceiling level during hot afternoon periods. Phase change materials installed at ceiling elevations capture this accumulated heat effectively, preventing it from radiating back into living spaces as surfaces cool overnight. The ceiling installation strategy captures substantial thermal benefits, with modest material quantities concentrated where temperatures rise fastest. Installation techniques include integration within drop ceiling systems, attachment to underside of structural ceilings, or inclusion within ceiling-mounted panel products. The wall installation approaches provide substantial thermal benefits, but at different effectiveness patterns than ceiling applications. Wall-mounted phase change materials interact with interior air through lower air movement rates than ceiling applications experience. The benefits accumulate more gradually but persist across broader temperature ranges. Wall installations also integrate more easily with standard construction practices, potentially at lower cost premiums than ceiling-focused applications. The specific application approach should match the building thermal profile and construction constraints rather than following generic recommendations that may not suit specific situations. Philip Henderson, a residential energy auditor who has evaluated performance of 33 homes incorporating phase change materials in the American Southwest, has documented patterns that inform optimal application approaches. His analysis shows that homes combining moderate quantities of phase change material with other passive cooling strategies, including ventilation, shading, and conventional thermal mass produce, better overall performance than homes relying primarily on phase change materials for cooling strategy. The integrated approach leverages benefits from multiple strategies while avoiding over-reliance on any single technology. The findings suggest that phase change materials function best as one element within comprehensive passive cooling strategies rather than as standalone solutions. The retrofit applications for phase change materials in existing homes offer somewhat limited but still meaningful opportunities. Phase change material installations during renovation projects when walls are already opened. For other work, add modest incremental costs relative to the renovation already underway. Replacement of existing drywall with phase change, drywall during remodeling, captures performance benefits during work that would occur anyway. Additions to existing homes can incorporate phase change materials at new construction cost premiums without affecting existing home portions. These retrofit opportunities allow capturing phase change benefits without the full commitment that new construction or complete renovation requires. The commercial building applications for phase change materials have developed substantially over recent decades. Office buildings with large cooling loads benefit substantially from peak cooling demand reduction that phase change materials provide. Retail facilities with daytime occupancy patterns match well with phase change daily cycling patterns. Educational facilities with predictable occupancy schedules enable optimization of phase change performance through coordinated building operation. The commercial applications have driven substantial product development that benefits residential applications through improved technology and reduced costs across the entire market. The future development trajectory for phase change materials suggests continuing improvements in cost, performance, and application flexibility. Emerging manufacturing approaches reduce per-unit costs substantially. New material chemistries provide phase change performance at temperatures matching specific applications. Integration with building information modeling and performance simulation enables sophisticated design optimization. The continuing evolution suggests that current applications represent early stages of broader technology deployment rather than mature endpoints. The energy grid implications of widespread phase change material adoption extend beyond individual homeowner economics. Peak cooling demand represents a major challenge for electrical grids during hot summer periods, driving expensive peaking power plant operation, and sometimes requiring emergency measures to maintain system reliability. Phase change materials installed across substantial portions of the residential building stock could reduce peak cooling demand significantly, reducing associated grid stress and power generation requirements during critical periods. The systemic benefits beyond individual buildings support policy initiatives that promote phase change material adoption through various incentive mechanisms. The compatibility with renewable energy systems produces synergistic benefits that neither technology achieves alone. Solar electric systems generate peak power during hot afternoon periods when phase change materials absorb interior heat effectively. The coordination of solar generation with phase change thermal storage allows coordinated optimization that reduces both heating and cooling energy consumption while maximizing solar utility. Homes combining solar electric generation with phase change thermal storage and appropriate thermal mass can approach net zero energy operation in appropriate climates at reasonable cost premiums over conventional construction alone. The product selection considerations for phase change materials require balancing multiple factors, including phase change temperature, latent heat capacity, cost per unit area, expected operational lifespan, fire safety performance, and integration characteristics with specific construction approaches. No single product represents the optimal choice across all applications. Informed selection requires understanding specific application requirements and matching product characteristics to those requirements. Consultation with specialists experienced in phase change applications typically produces better outcomes than generic product selection based on cost or marketing claims alone. Consider what implementing phase change materials means for families building or substantially renovating in appropriate climate zones. The additional investment produces a home with thermal performance characteristics that conventional construction cannot match. Cooling operating costs remain dramatically reduced throughout the home's lifespan. Interior comfort improves through more stable temperatures and reduced reliance on mechanical cooling. The environmental benefits include reduced electricity consumption and associated emissions. The maintenance requirements for phase change materials remain essentially zero beyond standard building maintenance. The technology has matured sufficiently to provide reliable long-term performance. The opportunity exists for families willing to invest in construction approaches beyond conventional norms. The evidence supports the performance across diverse installations and climate conditions. The product options continue expanding and improving. The obstacles are real but manageable for appropriate applications. The economic returns compare favorably to other high-performance construction investments. The long-term durability matches expected building lifespans adequately. The choice to incorporate phase change materials into new construction or renovation projects depends on specific circumstances, climate conditions, and priorities. The technology offers genuine alternatives to conventional cooling. Approaches with documented performance across thousands of successful installations. For appropriate climate zones and committed long-term owners, phase change materials represent a valuable technology worth serious consideration alongside other high-performance construction options. The ancient principles of thermal storage have evolved through space-age research into sophisticated contemporary applications that substantially extend what thermal mass approaches can achieve. The possibilities continue expanding as research and development produce further improvements.